All right, hello everyone, and welcome back to this Physics 8B live stream. Apologies for it being late this week. I actually got sick, lost my voice, had a bad cough, and all the conditions were there for the live stream to be terrible, so I punted until now. Sorry about that. We should be back on track with Thursday live streams moving forward. And the goal today is to cover electric potential. That's where we left off. And as a reminder, if it's your first time here and you haven't seen these before, basically the idea behind the live streams is to not repeat lecture, but cover the important topics from lecture. And so kind of bring what's important to the surface, perhaps add some clarity as we go. And then more importantly, learn how to solve physics problems. And so how do you go about setting up a problem and solving for it? And typically I do 2 or 3 problems depending on how much time I have and how long the problems are, to cover the different types of problems you might encounter, let's say. So we're going to do electric potential today. I'm actually going to start off with clarification about Gauss's law, something that I guess wasn't clear about how do you choose a Gaussian surface and why it matters and what the consequences are. So we'll start with that, and then we'll move on to electric potential, which is one of the chapters that most students hate. And there's good reason for that. It's abstract and you can't easily draw electric potential, unlike an electric field, which we can draw. So hopefully we'll find a way to just start talking about electric potential, and you gotta start somewhere. We'll start with some basics, and we'll try to build up from there. Perhaps not a perfect understanding of what electric potential is, but an understanding of why it's important and why you need it in this class. And then I think as you do more problems and as you practice, it will then become perhaps more obvious what it truly is and what it represents. But it's very hard to start with that and then do the applications. I usually find that it's easier to talk about applications first and to be practical. So let's go ahead and jump in here. And as a reminder, you can find the live stream in the free Physics 8B live stream course on slackademia.com. If you go to the study guide page, scroll to the bottom, the course is there. It's free to enroll. You don't need a credit card or anything like that. It's just a nice container with all the live streams, all the problems that I solve typed up that go with the live stream, as well as all the homework problems. So it's meant to kind of, build as you go, as you work through the semester. And of course, you can also sign up for study guides and master classes. Just master classes, heads up, it is limited seats because it's unlimited tutoring, so there can only be so many seats. And they tend to go pretty quickly, especially when midterms start showing up. So that's an alternative, but everything I do here is free and available in the Physics 8B live stream course. And of course, if you want to get in touch, there is a contact form on the website, but you can also DM me directly through Facebook. Is probably the easiest. And so if you're trying to get in touch with me, feel free to reach out through either, whatever's the easiest. So let's begin today with a quick clarification, perhaps, about Gauss's law. Okay, now Gauss's law says that the electric flux, which I'm going to write like this, but it doesn't really matter, because as we'll see, we typically don't have to worry about carrying out any sort of calculus. That's the beauty of Gauss's law. So the flux through a closed Gaussian surface of the electric field, so the electric flux basically, is always equal to Q enclosed, the amount of charge enclosed by the Gaussian surface, divided by epsilon naught. It's true all the time. It doesn't matter how wonky the surface is. Now the thing is, knowing that flux is equal to this is only helpful if I can do the following. I have to be able to go from here to here, where E dot dA is going to be E cosine theta dA. And that's just as a reminder, that's by definition of the dot product. If I have two vectors, if I have E and I have dA, and theta is the angle between the two. E dot dA is E cosine theta dA. Okay, so I want that to be such that I can do the following. Now from here to here is a definition. Now there's no requirement, that's just the same thing. But I want this thing here to be such that I can pull it out of the integral. So I need E to be constant in magnitude and direction on my Gaussian surface, because then I get to do the following. I get to go one step further, and I get to say E cosine theta. Then I'm just integrating dA over the area, which, by the way, is just going to be the area through which there's flux, is equal to Q enclosed over epsilon naught. And that's good because my goal in using Gauss's law is not finding flux. I don't really care what flux is. I only care that flux can be written like this so that I can solve for E. That's my goal. I'm using Gauss's law as a method to find the electric field. Now it turns out I can only do this when I have sufficient symmetry, this is why Gauss's law, even though it's always true, is not always helpful. Because if I have something that lacks sufficient symmetry, the best that I can do is say flux is equal to this. Now either I care what the value of flux is and I just compute Q enclosed over epsilon naught, but typically I don't, or I just enjoy complicated integrals over wonky surfaces, but typically I don't. I mean I do, but most people don't. And in either case it's pointless. As a chapter that sits right after electric fields, it's meant to be a method for you to compute electric fields easily for distributions or objects that have enough symmetry that you can find the electric field applying this method. So let's do a very simple example. In fact, an example for which we don't really need Gauss's law. We already know the answer. Right? I'm going to take the case of a point charge. Okay, so here's a point charge. Now a point charge, let's say it's positive in this case, is going to create an electric field that radiates away from it in every direction of space, including out of the page and into the page. Right, so everywhere, just kind of like a disco ball. And therefore the electric field has no preferred direction. So I'm going to choose a Gaussian surface that has no preferred direction. Now it turns out for 8b, it's always going to be a choice between a sphere and a cylinder with a top and a bottom, right? With end caps, if you will. It's one or the other. And those two get the job done every time. It's just a matter of choosing between the two. Okay, well, a cylinder has a preferred direction along its length. A sphere doesn't. And so to match the fact that the electric field has no preferred direction, I'm going to choose a Gaussian sphere. And I'm going to make sure that this sphere is centered on the charge, has a radius little r, and then I need to draw the outward normal, because it's a closed surface, like this. And if you look at any point on this sphere, you will see that the electric field E is always exactly along dA. That's the symmetry, right? Well, at least in direction. So the angle theta between E and dA is everywhere 0. Okay, so that's nice because then cosine 0 is the same everywhere. In addition, on the surface of the Gaussian sphere, everywhere you are is the same distance from Q0. So there is no reason why this electric field here should be stronger than this one here or stronger than this one here. That doesn't make any sense. We're the same distance from Q0 everywhere, so the electric field in magnitude is constant on my Gaussian sphere. So indeed, I can do the following. I can say that the electric flux through my Gaussian sphere, which is E, in this case cosine 0 dA, is simply going to be equal to E cosine 0, which is 1, so E, multiplied by dA integrated over the sphere, so that's just going to be the surface area of the sphere, which is 4 pi r squared. Okay, and then I can equate that to Q enclosed over epsilon naught by Gauss's law, and I'm going to get the result they already know about point charges, but that's okay. Q enclosed is just Q0, that's all there is. Okay, so then E is going to be Q0 over 4 pi epsilon naught r squared. Okay, so nothing new. I mean, I knew this before I even knew about Gauss's law, right? But that's not the point, okay? The point is to say the goal of Gauss's law is to find the electric field created by a charge distribution that has enough symmetry, and I can only do that if I'm allowed to make this step here, which is to have E constant in magnitude and direction on the surface of my Gaussian surface, or so constant in magnitude and direction on the Gaussian surface, basically. So I can pull it out and just say, okay, well, the flux just breaks down to E times area, which is kind of nice, or minus E times area if it's an inward flux. But the point is, I get my hands on E. That's what I want, right? So let's take the same example and let's address the question that I got, which was, it was a fair question. It's like, okay, you know, we say, well, you choose a Gaussian surface so that you can easily compute its surface area and its volume in case you need the volume to find the enclosed charge. So spheres, you know, cylinders, stuff like that. And someone said, well, a cube. How about a cube? It's like, okay, well, I mean, we could, you know, could try a cube, I suppose. You know, something like this where, after all, it's a closed surface. It's pretty easy to compute the volume. It's pretty easy to compute the area, so, you know, why does that not work? And fair question. I mean, you know, if you tell me the side length A, then why wouldn't I be able to do that? So let's take this and just draw the side view, because it's a little hard to see in perspective, but side view would look like this, right? Something like this anyway. And what you would get is the following. You would get the electric field radiates out in all directions, right? Now this doesn't look bad actually, because if then you say, well, how about if I draw the normal? Look, the normal dA is going to be along E. Well, it's also true here, right? And here, so it's kind of nice. I mean, you know, it seems like it's behaving like the sphere. Well, the problem is that it's not, because you drew 4 field lines. Let's just draw another, like for example right here. This is going to be the outward normal at this point here on the cube. So if I draw the field line that goes through that point, now this field line is going to look like this. It is no longer along dA. So is it true that theta is equal to 0 here between E and dA? Yes. But here, theta is not 0. So it's not going to be cosine 0 or cosine of some constant angle everywhere. It's going to be cosine theta. And as I integrate around my cube, cosine theta is going to vary. Even worse, this point here, where I have an electric field, is closer to Q0 than this point here, where I have an electric field. Which means that even though the difference in distance might not be very big, there's still a difference, so E here is weaker than here. And that's a problem, because now E is not constant in magnitude on the surface. So I can't even say this is a constant over the area that I'm integrating. So pull it out and, you know, simplify the integral. So here, the electric flux, phi E, cannot be simplified to E cosine theta A, because E and theta, the direction of E relative to dA, are not constant on the surface of the cube. Okay, so could you get through Physics 8b entirely without making this realization? Probably, right? It's not like it's a key realization, but it does help to understand why the cube fails when the sphere works in this case. Hopefully it cements why Gauss's law, as great as it is restricted, right? We can only apply it when we have sufficient symmetry, because it is very restrictive to say we want E constant in magnitude and direction over the entire surface that we're integrating on, right? So Gauss's law has certain applications. It works really well for the infinite line or the infinite cylinder, the infinite sheet or the slab, the point charge or the sphere of charge, solid sphere of charge, hollow sphere of charge, whatever. So for those symmetries, Gauss's law all day. For anything else, doesn't work. And even though we have the spherical symmetry here, you still have to pick your Gaussian surface properly. And in 8b, it's just going to be cylinder or sphere. They get the job done every time, you just have to pick the right one. Okay, excuse me. All right, so I thought that was a pretty fair question and something that, hopefully, again, it's not like vital knowledge, like you can get through the whole class without ever wondering. Just, if you do enough practice, you never see a cube, so why would you worry? But if you do ponder it, or if it does come up, then it's good to understand why. With that said, let us talk about electric potential. Now, electric potential, I've taught this for more of years than some of you have been alive, but electric potential, I have not found one way that just works for everybody and everybody gets it and makes sense and they love it. It's one of those chapters where I think what I've come to realize is that you just have to start with something. You just have to start talking about something that involves electric potential and kind of build from there. And then it's a little less mysterious what it is, and then you talk about it some more in a different problem, and it becomes a little less mysterious. And as you go, you just accumulate your knowledge, and eventually it kind of all comes together. But it's very hard to, from A to Z, present it in a way that makes sense. Because usually what happens then is that, your eyes glaze over because it's too abstract, which is fair. It's very abstract. It's unclear what the quantity is and why we need it. And so I'm going to try to explain why we need it rather than what it is. And we will say what it is. And, if it makes sense to you right away, awesome. But if it doesn't, just hang tight, do some more problems. You will see eventually you'll understand why V, the electric potential, is important. So this is going to be about electric potential. And let's start with this. I'm going to start with an electric field pointing from left to right. Okay. Now, what we've been told up until now is that electric fields go from plus to minus. Right? That's how we drew electric field lines. Away from positive charge toward negative charge, or away from positive charge all the way to infinity, whatever. But the point is, the electric field goes from positive to negative. That was our best description so far. Turns out it's not quite accurate, right? So I'm going to remove plus and minus, and I'm going to say that at these two locations, there are going to be different electric potentials. I'm going to call this V plus, and I'm going to call this V minus. And V plus is bigger than V minus, just to be clear. But it doesn't have to be that V plus is positive and V minus is negative. For instance, this could be 10 volt and 3 volt. Or it could be minus 2 volt, minus 12 volt. Or even it could be 8 volt and minus 3 volt, whatever. Only matters that V plus is bigger than V minus. Okay, so let's get rid of all that so that we can go back to our example here. All that matters is that V plus be bigger than V minus. And so the rule, the right way to state the direction of the electric field is to say that E points from high electric potential toward low electric potential. Okay, so E in general points in the direction of low V, or it points from high V to low V, or however you want to say it, it doesn't matter. E points in that direction. So that means that I now understand that there's a relationship between electric potential and electric fields. In fact, because 2 points have different electric potential, there will exist an electric field between them. There must. Right? If they had the same, if V plus were equal to V minus, there would be no E. So, what does V represent? Let's try to understand that. Now, I'm going to make this 5 volts. I'm just going to pick numbers because it makes things a little bit easier. And I'm going to make this minus 2 volts. And then I'm going to say that there's a charge Q, a point charge, 1 coulomb, which is a ridiculous amount of charge, but just to make the math easy, that's going to travel, starting at rest here, from left to right, and is going to have a speed V final that I don't know when it reaches this point, right? Now maybe we should label our points. Maybe we should call that point A, and this will be point B. Okay, so this charge goes from A to B. And as it goes from A to B, it speeds up from rest, and it reaches B with a certain amount of speed because traveled a certain amount of distance, and it's been accelerated by the electric force. So I can think of it in terms of force. All right, I know that the electric force is going to point in the direction of the electric field because Q is positive. That force will act between point A and point B, creates an acceleration, kinematics, I can find velocity, I can find how long it takes to reach point B, then eventually I can figure out how fast I'm going at point B. That's fine. I don't have a problem with that. But that's not why we need electric potential. Okay? We need electric potential because we want to define potential energy, and we want to be able to write conservation of energy for this point charge as it travels from A to B. Now, if you remember from 8A, conservation of energy is not a given. You have to only have conservative forces do work. And that was the weight force and the spring force for 8A. For 8B, there's a new conservative force, which is the electric force. And that force will be doing work from A to B. It's the only force acting on Q. And because it's conservative, we can apply conservation of energy to this point mass. Okay? Now, the only thing is, we had potential energy in 8A, it was mgh for gravitational potential energy, or maybe 1/2 kx squared for a spring. And if you ask me, well, what's the potential energy of a point charge? Like, well, I don't know. Like, okay, well, that's what V is for. Now, that helps understand what V is to an extent and why we need it. That does not tell me how I compute V. We're going to get to that. But if somebody tells me that it's 5 volt and minus 2 volt, then I can say that the initial potential energy of Q, if V plus is the amount of energy per charge at point A, then I take the charge Q multiplied by V plus, and I get 1 times 5 is 5 joules of potential energy. Potential energy is energy due to position. It can be spent by the particle to acquire kinetic energy, which it does. As it travels from A to B, we'll see that its potential energy gets depleted. U final here is going to be, well, the potential energy at point B is the amount of charge Q multiplied by the energy per charge at point B, which is V minus, and that's going to be equal to 1 times minus 2 is minus 2 joules. Okay, so at point B, the particle has less potential energy than at point A. It spent 7 joules to acquire kinetic energy. Now you might say, well, hold on. Seems like, particle went a bit crazy and overdrafted, right? And not negative potential energy. Yeah, that makes sense. It's like, well, it doesn't matter, right? Something you might remember about potential energy from 8A is that it is the change that matters, that makes sense. It is not the actual amount. So whether this is 5 and minus 2, or whether it's 10 and 3, the difference is 7, and the difference is what's meaningful, right? So it can be negative, that's fine. We're not going to worry about that. And if you recall, conservation of energy from A to A, it's kinetic energy at point A, 1/2 m VA squared. Now that's 0 because Q starts at rest at point A, so it has no kinetic energy. Plus the potential energy is Q V plus is equal to potential energy at B is 1/2 m VB squared plus QV minus potential energy, right? Okay, this is what we want to be able to do because it's a lot easier to find VB like this than to use Newton's second law in kinematics, right? I'm not saying it's not possible to do second law in kinematics. I'm saying most of the time it's a nightmare. So if I throw QV minus to the other side, factor Q out, I get 1/2 mVB squared is Q times V plus minus V minus. And yes, I know what that is, so I can solve for VB and all that, right? I can multiply by 2, divide by m, square root, all true, right? So I'll just write it to take this thing the whole way through, right? Because we said we wanted to find VB, so just so that I don't lose anyone here at this point, that then says, well, you didn't solve for VB, which would be fair, I didn't. But the point is I can, right? That's the point. So we kind of know what V is, kind of. Like, V is this thing, it's a property that surrounds charge, because E is a property that surrounds charge, and E points from high V to low V, so there's got to be a relationship. And V at any given point is the amount of potential energy per charge. So if I take V and I multiply by Q, like I did here, I get potential energy at that point for that charge. So, okay, I guess. Point is, I want to be able to do this in this chapter. I want to be able to find what this is, V plus minus V minus. There's two ways to do it. I can either evaluate the difference in and of itself directly, or I can find V plus, separately find V minus, and then I could subtract them. Two options. The former is what we're going to focus on the most because it's related to the electric field. The latter is slice and dice, and we will do an example of slice and dice in the end. So here's the thing. Let's first clarify some vocabulary, and then we'll figure out how to compute this difference, V plus minus V minus. But the idea here is that we have what's called, well, what is it? V is electric potential, so this is an electric potential difference, right? It's the difference between V plus and V minus. Okay. Now, an electric potential difference is called a voltage. Because nobody's going to say electric potential difference. You're like, oh no, okay, we get it. Like, please, can we have a simpler word that means that? So, a voltage is a difference between two values of V, where V is electric potential, right? So, in and of itself, V, either one of these, V plus or V minus, is just electric potential. Not to be confused with electric potential energy. That's U, that's Q times V. Okay, careful, words are really tricky here. So, V is electric potential. If I take V plus minus V minus, that is a difference in electric potential, or an electric potential difference. And nobody calls it that, we just say voltage, because, it's easier. The problem is, then we get loosey-goosey. And we're like, oh, what's the voltage V plus? You're like, no, wait. V plus is potential, or electric potential, not voltage, right? But the thing is, if you do this all day, you get loosey-goosey, particularly when it comes to this. Usually physicists are pretty anal about words, but here they're not. So we'll call V potential, whereas we should say electric potential. But then we'll also call it voltage, whereas we should say electric potential, whatever. Like, it's very loosey-goosey. It's very, it's kind of, however it comes out is what we're going to use. But if we want it to be very specific, we would discriminate between V, which is electric potential, and V plus minus V minus, which is a difference in electric potential, and that's a voltage. Okay, so sorry, I didn't mean to harp on that, but I get so many questions later on in the semester because we didn't clarify vocabulary off the bat that I try to clarify it up front now. So anyway, that's why I want to know how to compute V, right? And again, if V is still mysterious to you as to what it is, because you can't draw it, it's a number, right? What are you going to do? Just roll with it. And if it helps, every time you see V, just remember it's potential energy per charge at that point. So what that means is if you multiply Q by V, you get potential energy. Right? And that doesn't help understand what V is, but eventually you'll get there. You'll get more comfortable with the concept. Okay, so now let's learn how to compute V plus minus V minus. And we're going to do this in problems, so I'm not going to spend too much time on it. And I'm going to try to organize this in a way that then makes sense when we go do problems. So this is the relationship between E and V. Okay. Now, this is the most butchered formula in physics AB of all time. It doesn't matter which semester you look at it. At some point you're going to be off by a minus if you're not careful. So V plus minus V minus is going to be equal to minus the integral from minus to plus of E dot dr. Okay. And we're going to learn how to apply this when we do problems. But I'm going to box this, and I'm going to insist that you memorize it perfectly, minus out front here included. Don't start messing with the bounds and saying, oh, minus the integral from A to B is the integral from B to A, because eventually you're going to trip on yourself. This is what the formula is. When you see a problem where you need to apply it, you just write it like that. And then you start figuring out what's V plus, what's V minus, what's E and all that, and you figure it out. But if you don't very carefully write things in the right order, you're going to forget something. Okay, so don't forget the minus. Sorry, that's not what I wanted to do. Don't forget the minus that's out front. It is there because E points in the direction of decreasing V, right? And an increase, technically if you point in a certain direction, you expect it to increase. But E goes the other way. So because of that, just because of direction, there's a minus out front in this integral, okay? Then if this is V plus, if V plus is your first term, plus has to correspond to the upper bound. Minus V minus, if V minus is your second term, the minus has to correspond to the lower bound. Okay, not gonna lie, in my brain, this is literally how I see it. That is what my brain does. Works for me. It doesn't work for you, that's fine. But don't mess up your bounds. The order on the left has to match the order of the bounds and vice versa. You can't just do whatever the hell you want. Okay? And again, I get it. Like, this formula doesn't mean anything right now. Right now, we're holding an empty sack. We're like, great, we have a formula. This is as helpful as F net equals MA in 8A. When they're like, hey, F net equals MA. Didn't mean anything until we did 5 problems with F net equals MA. Not going to mean anything until you do 5 problems with this formula and you start to realize why you need it and how you apply it. Okay, but the goal is to compute the difference V plus minus V minus so that you can do conservation of energy calcs, okay? And the way you do it is you relate this to the electric field, which means that, hey, wouldn't it be nice if we already knew the electric field? Well, isn't that handy? We just spent 3 weeks figuring out how to compute electric fields, either by superposition, by slice and dice, by Gauss's law. So we have a lot of tools that allow us to compute electric fields. So very likely you would have the electric field, or you would be in a position to compute it, so that then you can find V plus minus V minus. But bear with me, we're going to get to this in a problem. So this is the relationship between E and V. The formula doesn't have a name, but that's how I call it, and that's a formula in and of itself. That's one option, right? I said you can compute the difference, V plus minus V minus, cool, or you can compute V plus, you can compute V minus separately, and then you could subtract the two. Not as common, but doable, okay? So if you wanted to compute V directly, okay, option 1 is the easiest. in the case of a point charge, we're going to give you the formula for V. So if this is a point charge Q, and this is a location, a distance r away, so this is a point P, but there's nothing at P, right? It's just a location in space. Then the same way that I know the electric field created by a point charge, I'm going to be given the electric potential created by the point charge. That's KQ over R. Alternatively, if you prefer, it is Q over 4 pi epsilon naught R. I don't care. It's in volts, right? And it's positive or negative depending on whether Q is positive or negative. But that's V for a point charge. So if you had an electric field created by a point charge here, right? If this E were created by a point charge somewhere over here, well, you could say, you know what? It could just find V plus on its own, V minus on its own, and I'd subtract them directly. I don't have to do this. I could, but I don't have to, right? Because I have a formula that gives me V. That is the only formula that you will have that directly gives you V. All right, same thing for electric fields, right? Remember the first week, or maybe the first 2 weeks, we said E is known for a point charge, that's all. For anything else, what do? Slice and dice. We take a slice so small that we treat it like a point charge, but then we integrate over the object to get the full electric field. Okay, well then, same thing here, right? Slice and dice. And I'm going to write it, you should almost not even write it like this, but the point is you're going to integrate K dq divided by R. And that, again, is a formula that means nothing until you see it in practice. But just to understand, if we want to evaluate V directly, the only formula we have is this one. Slightly harder, I could do slice and dice, and I might get V everywhere with that. But most of the time, if I know E, the electric field, then I can get the difference, the voltage V plus minus V minus, by knowing E. All right? So hopefully that's fair. I'm going to jump to the problems that I want to do today. I'm going to do them, well, I had an order in mind, but I'm going to switch it up. I'm going to follow the same order as these things. So I'm going to start with this guy, all right, applying that, see how that goes. Then we're going to do one with point charges, so we can use KQ over R, and then we'll finish with a slice and dice, okay? So let me, just give me a sec to reshuffle stuff, and then I can go ahead and dive into this guy. There he is, this guy here. Okay, so this one's kind of a cool application where we have this hollow metallic cylinder that's really long, has charge per area sigma, and first we want to find the electric field everywhere. That's Gauss's law. And then we want to figure out if we launch a point charge minus Q toward this positively charged cylinder, how fast does it hit the cylinder? Because it's attracted to it, so it's going to hit the cylinder. And in practice, this is actually how you paint planes. So if you have your plane, you hook it up to a certain electric potential, and then if you can make sure that your paint droplets have, let's say, a negative charge, and that your plane is at a positive potential, then instead of making a big cloud of paint, because it's a lot of paint for big planes, the cloud is just going to kind of get sucked onto the cylinder because of electrostatic forces. So it prevents from making too big of a big, paint mist in your hangar and getting everything all messed up, and to paint very accurately in a clean way planes. So it's a cool application, but the goal again is to say, okay, well, let's find E everywhere, and then we'll find V plus minus V minus to do conservation of energy in this problem part here. Okay, so this is Gauss's law. You have to find the electric field everywhere. It's an infinite cylinder of charge for all practical purposes. And so I know that to find the electric field everywhere, I'm going to first have to find it inside the cylinder, and then I'm going to have to move outside, because there's two regions. There's inside the cylinder and outside. Okay, now if I'm really good at Gauss's law, I already know the answer. I know that in region 1, in here, there will be no electric field because there's no enclosed charge, right? It's a hollow cylinder. So if I take a Gaussian Now it looks like a sphere, but careful, it's a cylinder, yeah? A Gaussian cylinder, like this, okay, with a certain length L, right? If it helps, you can do this, right? Just, okay, this has a length L, and then so does this, etc., etc., right? So just to visualize that we're dealing with cylinders and not spheres, right? So that we get the area right, okay? But so if I have an infinite cylinder of charge and I compute the flux through the Gaussian cylinder, I expect there to only be flux through the cylinder wall. It is going to be E1, let's call it, times the area of the Gaussian cylinder wall, right? So this part, not the end caps, just the wall. And that's going to be 2 pi r L, okay? And then Q enclosed over epsilon naught, well, that's actually super easy. There is no charge inside my Gaussian cylinder because my charge lives on the actual physical cylinder, the metal cylinder, and within it, there's nothing, there's just air. So inside this Gaussian cylinder, there is no charge whatsoever. Therefore, by Gauss's law, E1 is equal to 0 for R less than R. Okay, I would say on my exam by Gauss's law, for that matter, right? I didn't write it here, but on the exam, I definitely would say how I know this. So that's easy. Region 1, plus we don't care. I mean, the paint's going to be in region 2. It's going to be outside the plane, and then it's going to land on the surface of the plane. So this is kind of just, for good form. Really, we only care about E in region 2. Okay, now in region 2, it's pretty straightforward. The cylinder is positively charged. E2 is going to leave the cylinder radially like this. And if I take a Gaussian cylinder that now has to live in region 2, then E is going to be along the normal everywhere on the cylinder wall. And so the flux will be the same. I mean, the difference is that it's going to be E2 times 2 pi RL, but that doesn't change really the form of it because flux doesn't care which region you're in. It just cares that you're computing it through a cylinder. Okay, now Q enclosed over epsilon naught, that is a different story in this case. I'm going to have an amount of charge per area sigma. Now I have to multiply that by the actual area that carries charge, right? So if this is my cylinder, has a radius big R, length L, then 2 pi big R L is going to be the amount of charge, well, the surface area, which multiplied by sigma is going to be the total charge enclosed by my Gaussian cylinder, right? So that's the amount of charge that lives in the Gaussian cylinder. Don't forget epsilon naught. By Gauss's law, we have E2, 2 pi RL is equal to sigma 2 pi big RL over epsilon naught. 2 pi L goes away. Makes sense. The answer should be independent of L if it's truly an infinite cylinder. And then E2 is going to be sigma big R divided by epsilon naught little r. That is for little r greater than or equal to big R. Okay, and this is radially outward for that matter. So we should specify direction like that. Or you could use our hat, whatever, doesn't matter. But the point is, magnitude and direction of the electric field outside of your cylinder. Okay, and that first part is just Gauss's law. So this makes this a very good exam question. Right now we've tested Gauss's law. Now we get to see how you do with conservation of energy for this thing, right? How fast is this charge minus Q going to hit the cylinder's surface? Okay, starting from R is equal to 3 big R. Okay, so let's paste this down here, make it a little bigger maybe just for clarity. Okay, and what do I know? Well, I know E2, yeah? E2 is radially outward. In magnitude, I've just figured out that it's sigma r over epsilon naught little r, so I know that. And then I'm going to look at this particle as it begins here and ends here as it reaches the cylinder and strikes it. It strikes it with a speed v final, which is not zero. Speed is zero after striking the cylinder, but when it comes and hits the cylinder, it has a certain speed. Okay, speed upon impact is never zero. It's after impact, maybe, but not on impact. So that's what I have, and just to be clear, I mean, this is how I would draw it just for my own sake, but this is going to be R is equal to big R, and this is R is equal to 3R, right? And then probably we're going to need the electric potential, right, here. So that's going to be V initial, and here it's going to be V final. Right? I don't know what it is, but if I can compute the difference because I know E, then I should be in good shape, right? So let's start with conservation of energy. And then we'll see that what we need to do is find V final minus V initial. Okay, conservation of energy states that kinetic energy at the initial point, 1/2 mv0 squared, plus potential energy. Okay, potential energy, remember, is charge, minus Q in this case, times V initial, is equal to 1/2 m V final squared plus minus Q V final, right? Now I want to solve for this, right? So I'm going to get that 1/2 of m V final squared is equal to 1/2 of m V0 squared plus Q V final minus V initial. Just to be clear, I added I added Q V final on both sides, just factored it out because I had minus Q V initial here. Point is, I could keep going, right? But at some point, I don't know what this is. I need to know what that is. Okay. So I'm going to figure out what that is, and I'm going to do what you're going to see in answer keys most of the time. See, when we write answer keys, we already know we're going to need this. So a lot of times, because we don't want to interrupt conservation of energy in the middle, we just say, well, I know I'm going to need V final minus V initial, so why don't I just start by computing that? Okay, and then you read the answer key, and it's like, well, how the heck did he know to do that? It's like, just practice, that's all, right? And I don't want to like do this and be like, oh, JK, I have to stop here, then I have to go do this, and then I can continue. So instead, we start with V final minus V initial, and then we plug it into conservation of energy later on. All right, so if you see that, don't be surprised, that's what's going on. But I want to make some room because I want to refer to the figure as I set this up. Okay, so first things first, I don't want to butcher the formula, so I just write it out as is. It's going to be minus, just because there's a minus. If V initial is the second term, then it's the lower bound. V final, the first term, it's the upper bound. E dot dr. Okay. All right, now we should draw dr. Okay, this is dr. And you might say, well, dr goes the other way. Why does it? I thought the particle goes from right to left. Why does dr go that way? You have no choice. Dr points in the direction of increasing r. Full stop. Okay? So make sure you keep that in mind. It's important. Because what we're going to do now is say, okay, well, this is minus the integral E dot dr. This is similar to E dot dA. from before in the sense that it's a dot product. So it's going to be E cosine theta dr, where this time, just to be clear, theta represents the angle between E and dr, right? Between the two vectors involved in the dot product. It used to be dA, now it's dr, whatever. And so, okay, so then E in magnitude is sigma r over epsilon naught little r. Cosine of the angle between E and dr is 0. They both point in the same direction. I guess I should do this. The right way to do it is like this. E2, my bad. Should do that. There we go. Okay, and then dr. Okay, and then like, well, apparently what I'm doing here is I'm going to have an integral in terms of r, and the dr indicates that I'm integrating with respect to r. So what does initial stand for? Well, initial stands for this location here. So then the bound here is 3 big R. Final stands for this location here, so the bound there is big R. Okay, and now I've set up my integral properly. I didn't try to take any shortcuts. I just said, start with the definition, plug in what I have, and now you can go ahead and have some fun and do the calculus, right? So then this is going to be, integrals don't care about constants, so minus sigma r over epsilon naught. You're integrating dr over r. The antiderivative of that is natural log of r between 3r and r. Okay, now that's going to be minus sigma r over epsilon naught natural log of r minus natural log of 3r, which we can simplify further because if we absorb, or if we distribute the minus, right, within the into the parentheses, then we get this, and ln of 3r minus ln of r is really just ln of 3r over r, so that's natural log of 3, right? Remember that natural log of b minus natural log of a is natural log of b over a. Okay? So that's v final minus v initial. And the only way I figured out what it is because I first was able to figure out what the electric field is. Okay? So then I can take that and I can plug it into here, and I can say that, let's just do this so that we don't go too fast. This does not change, plus, well, q, then sigma r over epsilon naught, natural log of 3. Okay, so we're going to multiply by 2, divide by m, and then square root. So we're going to get v0 squared plus 2q sigma r over m epsilon naught, natural log of 3, square root that. Well, that is how fast the charged paint particle or droplet hits the cylinder if it's, initially launched with a speed v0. Okay, so yeah, is it easier to understand what v is? Maybe not, but at least understand why we need it. We need it to apply conservation of energy. All right, so that's to illustrate how to use that formula. V final minus v initial is minus the integral of E dot dr. So let's now look at this problem, which is actually a nice review of a whole bunch of different things. But it allows us to use the formula kq over r for the electric potential created by a point charge, and so that's always nice. We have 2 point charges 3 meters apart, and then point C 3 meters to the right of B. And we know QA, QB. Okay. What is the magnitude and direction of the force on the charge B due to A? Okay, so that's, it's not free points, but almost. This is just, something we could have done week 1. But it's okay. It's a good problem because it's going to review all that, right? So this is A. this is b. And, I mean, I'm just going to call the distance between the two r. It's 3 meters, it turns out. Right? And then, okay, we want to find what is the magnitude and direction of the force on the charge B due to charge A. Charge A will attract charge B, right? This is going to be the force of A on B. It will point to the left, and it will have a magnitude given by Coulomb's law, right? So F of A on B is going to be equal to K QA QB divided by R squared. I should just be careful because QA is negative. So really, if I want magnitude, I have to throw some absolute values in here, right? And that's going to be equal to 9 times 10 to the 9, that's K. QA is minus 2 times 10 to the negative 9. QB is 4 times 10 to the negative 9, divided by 3 squared, which is 9. So this simplifies nicely. 9 cancels with this. 10 to the 9 cancels with 10 to the minus 9. And we're going to get, these should be absolute values, my bad. Okay, we're going to get 8 times 10 to the negative 9 Newton to the left. Or you could write it along minus x hat if you want, that's fine. If you wanted to write it as a vector. Okay, so that's easy. I mean, that's not even anything that has to do with electric potential. Okay, so let's then continue with what is the electric field strength and direction at point C, which is 3 meters to the right of point B. Okay, so let's take this thing here, get rid of that. All right, so at point C, which is just a location in space, what is the electric field created by these two charges? Well, this is superposition, right? We've done this before. Just account for the electric field created by A, account for the electric field created by B, and then properly add these vectors together, right? Excuse me. Okay, so A is a negative charge. It is going to create an electric field EA that points left. B is a positive charge. It will create an electric field that points right. And I'm going to choose to the right as the positive direction. I'm going to say that E net at C is going to be EB minus EA. Okay, now that's going to be K, absolute value, well, no, piece positive, so KQB divided by, now careful, it's 2R squared. No, it's not. Wow. Sorry, my brain really wanted to do QA first, but we're doing EB, so duh, my bad. KQB over R squared is the magnitude of EB, points to the left, to the right. And then to the left, EA is K, absolute value of QA, divided by, now careful, now the distance between QA and C is 2R, gotta square that. Okay, there we go. Okay, so then at this point it's just a matter of plugging stuff in, okay, which shouldn't be too bad, hopefully. This is going to be 9 10 to the 9 multiplied by 4 times 10 to the negative 9 divided by, well, 3 squared minus 9 10 to the 9 multiplied by absolute value of minus 2 times 10 to the negative 9 divided by, now 2 times 3 is 6 squared is 36. All right. And so this is going to be, well, 10 to the 9 and 10 to the negative 9 are going to cancel. And then this isn't be 4, because 9 over 3 squared is 1. And then minus, well, 4 times 9 is 36. So 4 minus, oh, there's a 2 here, my bad. So this is 18 over 36, so minus 1/2. Okay, so this is going to be 3.5 Newton per Coulomb. And it's positive, so it's going to be to the right. All right, that's the magnitude of the electric field at point C. The direction is to the right. Okay. Question 3, what is the electric potential at point C? Please use the convention that V is 0 very far away from the charges. Okay, so this becomes interesting. Now we can start talking about electric potential. Okay, so we're back to this thing here. And see, electric fields are nice because at least I can draw them. I mean, they're abstract. I've never seen one in real life, but at least if I'm dealing with them, I can draw vectors. Electric potential, I can't draw anything because it's just a number, right? So by superposition, at point C, the same way that we did superposition for the electric field, the electric potential at point C is going to be VA plus VB. Now remember we said V for a point charge is KQ over R. Could be positive or negative, right? You have to account for that with Q because it matters if V is positive or negative, right? So for A, if I start with that guy, it's going to be K QA, but not an absolute value, just QA, divided by 2R, because that's the distance, plus K QB divided by R. All right, so that is 9 times 10 to the 9, multiplied by minus 2 times 10 to the negative 9, divided by 2 times 3, plus 9 10 to the 9, multiplied by 4, 10 to negative 9, divided by 3. Okay, so then this cancels this, like that. And then the 2's go away. And I get minus 9 over 3, which is minus 3, plus 9 over 3 is 3 times 4 is 12. So I get 9 volts. And it's a number, so there's no direction, right? It's just that's the value. Right. Okay. So that's the electric potential at point C. All right, so VC is 9 volts. And we're told that infinitely far away, V infinity, is 0. Okay. So now a third point charge, QD, with 3 10 to the negative 9 coulomb of charge, is brought to point C from very far away, so from infinity, and held in place. How much work does this require? Okay, so we're saying that QD started here, and it's brought, oof, that's bad. It's brought all the way over to here, right, and held in place. How much work does that require to do that? Okay, now this is an interesting question. It's a pretty classic question, actually. The work required by a person or by a force F or whatever you want to call it, the work done by the person, by you, is equal to the change in potential energy. That is what you're doing, right? You're taking something that's infinitely far away, where it has no potential energy because the infinity is 0, and you're bringing it up to point C. Now QD is positive, VC is positive. If you multiply the two, you get a positive number, which is the potential energy of QD at point C. You had to give it that amount of potential energy. The analogy is you took a crate from the bottom of the hill and you pull it up to the top of the hill. Now it has potential energy mgh. Well, the work you did is mgh total. That's what you had to do to bring it up to the top of the mountain, right? So the work done by the person is going to be the change in electric potential energy for QD. Okay, well, delta U is QD delta V. Okay, that's QD. Delta V is VC minus V infinity. V infinity is 0. And so this is going to be equal to QD times VC. Now QD is 3 times 10 to the negative 9, multiplied by VC, which we know is 9. So this is 27 times 10 to the negative 9 joules. Okay, not much, arguably, but also there's not that much charge on QD, right? So that's why. So the goal there is to illustrate, that electric potential can be derived, first of all, can be derived from the formula if you have point charges, KQ over R, and you can use superposition to find the net electric potential at a point. But still, at that point, 9 volts represents 9 joules per coulomb. So that eventually, the electric potential energy of QD at point C is VC, the 9 joules per coulomb at that point, multiplied by the amount of coulomb that I put at that point, right? That's going to give the potential energy. So when you're manipulating electric potential, that is what you're manipulating. You're manipulating a certain amount of potential energy per charge, and really the only goal is to get potential energy. You multiply QV, right? And I think the problem with electric potential is when we present it to you, we start to say, oh, electric potential is this, and this is how you get it, and you do slice and dice, or you do this. And we present to you all these ways that in the space surrounding charge there's an electric potential, and all the ways you can compute it, or you can at least compute the difference. But we don't emphasize what the end goal is. The end goal is, most of the time, conservation of energy. Now, could you have a problem on an exam where the only goal is to compute V? Sure. We're going to see that in the fourth problem. It's going to be slice and dice. But, in general, what you're trying to do is you're trying to find V because you want to make an argument about, most of the time, conservation of energy, right? How the potential energy of the particle got spent to acquire kinetic energy, or the other way around, and then maybe how fast the particle is going or something like that. In some cases, how far you could solve for that. There's some good exam problems about that. So again, I appreciate that V is an abstract quantity. We can't draw it, it's just a number. And it's, I don't know, maybe intimidating is not the word, but it's unclear what it's used for off the bat. If you can keep those few things in mind as you work through problems, I think you'll come to like electric potential quite a bit, because it is a lot easier to solve this type of problem than it is to solve some of the other ones we've done. I mean, again, it's just a number, so it's very easy to get. I don't have to worry about direction like I do with vectors. All right, so then our last little exercise of the day, there we go. So remember that I said I was going to do them in the same order that I presented them, and I had ended with slice and dice, and so here is a slice and dice problem. Now you might recall the ring of charge. We did it for, we didn't do it, but it's a classic, and I think it was on a homework, it could be wrong. We did the semicircle of charge, I'm pretty sure. But the ring of charge is a classic slice and dice problem. It was definitely done in lecture with Spilio. And I would be shocked if Bordell didn't do it too, because she really likes it. We did it for electric fields, is my point. And slice and dice is not specific to electric fields. Slice and dice is a method where you take these little slices, you find the contribution of one of them, and you integrate over the object. It doesn't have to be for an electric field. Could be for electric potential, could be for a whole bunch of other stuff, could be for magnetic field. So it's a method that is a general method. And here we're going to use it and see how it applies to electric potential. And again, we're going to be pretty happy with ourselves because electric potential is just a number, so it's a lot easier to deal with. than electric fields. So I'm going to try to do this in a way that kind of mimics how you might have seen it with the electric field so that it's easier to follow. But you have a ring, it has a radius r, it carries charge per length lambda, and you want to find at point P, which is a distance L away, what is the electric potential. Okay, and all right, so I'm going to do this. All right, this is going to be, if you look down like this, you will see this ring, right, and it has a charge per length lambda. Now I'm drawing it like this so I can do the following. I want to draw a tiny slice, right? Now I'm going to draw it big enough so that we can see what we're doing, but it's a tiny slice of length ds, and ds is going to be, if this is r and this is d theta, ds is r d theta, right? And what we should say is that theta, you can set the origin wherever you want, but let's set it here like we do in math. This is theta equals 0. And the slice in question is at some arbitrary theta somewhere. And what I'm trying to get at is eventually we're going to integrate around the ring over theta to find the net electric potential at point P. But right now I want to be able to just use my little slice here of length ds, which therefore has charge dq, is lambda times ds, right? Because lambda is charge per length, so times the tiny length, I get the tiny charge dq. And I want to find how much electric potential this thing creates at point P. Okay, well, the argument of the slice and dice method, first let me just to be clear, this is little r, it's square root of r squared, big R squared, plus L squared. Okay, slice and dice, the argument is to say, my slice is so small that I can treat it like a point charge. Why is that good? Because at least I know the formula for the electric potential created by a point charge. So this dq is going to create at point P a tiny contribution to the electric potential that is going to be given by kq, which is really dq, divided by little r, right? Now that is k lambda, ds is r d theta, divided by the square root of r squared plus L squared. Okay, that's just the contribution from that little slice. How do I get the full contribution of the ring? I integrate around the ring over theta. Okay, so I did it here so that we could do it on the figure. V at point P is going to be the integral from theta equals 0 to theta equals 2 pi of this thing. Okay. Oops. Let's grab the little hat for pi there. There we go. And this is actually an incredibly easy integral to compute because everything is constant. K and lambda are constant, r is constant. This is constant as I go around the ring. It's not a function of theta. Any point on the ring, doesn't matter which one I take, is going to be a distance little r from point P, right? So this is k lambda r over square root of r squared plus L squared, integral from 0 to 2 pi of d theta. Integral of d theta is theta. Evaluate between the bounds, you're going to get 2 pi minus 0. So this is going to be 2 pi k lambda r divided by square root of r squared plus L squared. That will be the net electric potential at point P, right? And so what it means is that, you know, if you go back to point P is defined by its distance L from the center of the ring, right? So, you know, if you have another point down here somewhere, well, you just have a different value of L. So what you've done is you've found V everywhere on the axis. So if then you want to apply conservation of energy between 2 points on the axis, you can say V final minus V initial, but you just have a formula that you can plug in directly for V. You don't have to relate it to the electric field. You could, but it's harder. And so it goes back to what we said before, right? Like just to illustrate, because it's nice to talk about stuff, but it's a lot easier with drawings, right? So this is P. P is at x equals L. And this is Q at x equals, I don't know, D. It doesn't matter. I mean, actually, no, L plus D. Let's do that. All right, so this is D. Okay, and this is L. Okay, and what if you wanted VP minus VQ, or VQ minus VP? It doesn't matter. Now, you could do this. You could say, oh, it's minus the integral of E dot dr, and then I know how to get E. I did it in lecture. It's the ring, slice and dice, boom. Now, do I want to go do slice and dice again to get E, which is harder because it's a vector, for a ring? Probably not. Like I could, but probably not. So that's an option, but I'm not going to do that. Instead, I'm going to say, okay, well, look, I just figured out V at point P, right, when we're a distance L away. So it's going to be this, that's VP, right? And then minus VQ. Well, what's VQ? Well, VQ is the same thing. It's 2 pi k lambda r divided by the square root of r squared. The only difference is that instead of L, it's L plus D, all right? So when I was saying earlier, there's two ways to compute the difference. You can say the difference is minus the integral of E dr. Okay, that works if you know E, or if it's easy to find E. Or perhaps you're able to find just a formula for V, right? If it's a point charge, you already know what it is, but if it's a ring, here you've derived it. And then if you want to evaluate the difference, well, you just plug in VP and then minus VQ, and that's it, and you're done. So I'm doing this just to emphasize the overview of what is V, why do we need it, and how do we get it is the most important part. And it seems to me that a lot of times books and in lecture, we start with how do we get it, and then maybe we get to why we need it, and it makes it really hard because you end up doing all these calcs like this to find a quantity that you're not even sure what it is or what it's for. So I'm not saying my method's better. I hope it clarified some things. I know that it doesn't really matter which direction you attack electric potential from. Usually it's a chapter that students struggle with at the beginning. My view over time has been to say, look, you just start somewhere, start learning something about it, keep going, keep going. You'll see eventually, if you do enough problems, you'll accumulate enough understanding that you'll get comfortable with it. But there's no perfect way to introduce it and to, get you to fully grasp it immediately. I think it's just one of those things that needs to sit a little bit. You need to see it applied in different scenarios. And, there's a lot of information coming very fast at you in AP, and so this one needs a little bit of time to be digested, really. So anyway, hope that helps. Thanks for watching, as always. Thanks for your questions and for, keeping in touch. And for those of you who send me the homework PDFs, appreciate that. Thank you. Feel free to do so if you see a homework posted that is not solved online. And if you need help with Physics 8B, again, there's the study guides, there's the masterclass. Always happy to help you out if I can. But if this is enough and you can get what you need out of that, then that's great. But midterm's coming up fast. Make sure you spend some time on 8B, because by the time midterm has arrived, by the time you get there, you will have covered a lot of ground, right? Electric fields, Gauss's law, electric potential, capacitors, probably circuits, at least in part, sometimes even magnetism. You'll see some old exams have one magnetism problem. That really depends how fast lecture moves. It also depends if the two professors sync up and decide that they're going to cover it or not, or it also sometimes depends on when the holidays fall relative to lectures. So it could be all the way through part of magnetism, right? That's a lot to chew on. And these are complicated things that are not intuitive because we don't relate to them in everyday life, and just take time to kind of understand. Anyway, I'll shut up because it's time to go. Thanks again for watching. Sorry this live stream was late. I should be back on track with regular Thursday postings, and have a great week. and best of luck with physics.